Excellent. Okay. I apologize for that. Thank you so much for having me here. Thank you, Pablo, for the introduction. My name is Craig Arnold. I'm in the Department of Mechanical and Aerospace Engineering, and also with Princeton Institute for Science and Technology and Materials. And today I want to tell you just a little bit about the kinds of things we do in my group related to energy storage, particularly things related to how we can optimize electrochemical energy storage devices. Think of things like batteries or capacitors and such like that. And what we're going to do is we're going to try to meet some of these challenges by understanding the nanostructures, how we can optimize them, understanding the mechanics and how that relates to the electrochemistry, and also doing some advanced laser processing type approaches to see how we can further optimize these systems. First off, my group, as well as the funding agencies, particularly I want to thank Elena and Christina, two of my students who are doing much of the work I'm talking about here. Now, clearly energy storage is important. I don't need to give you a full background on this. You can think of a variety of reasons why you care. A car, an iPhone, wind power, all of these things, right? If it's wind or solar, the wind isn't always blowing or the sun's not always shining. There we go, good. So you need to worry about how you might load level these types of systems. In other cases, you might think of having a need for extra energy. In the case of the iPhone or a car or something, you might think of something being portable. And finally, perhaps most importantly, is that novel systems require novel solutions. And you know, the constant question I get is, well, can you just make a single battery? Can you make some magic system that will solve all of our energy needs? And the answer is well, it's not that simple, because each particular system has particular demands that we have to meet. And so one has to look at different things, such as, should the battery be flexible? Does it need long life or lightweight, or other types of metrics that you care about? And so clearly energy storage is one of the key challenges we faced in the 21st century. But also, you might think of, say, semiconductor or electronics, and we think of something like Moore's Law, where the storage capacity in a computer doubles every 18 months. Well, unfortunately for batteries, that doesn't quite work. In the case of batteries, the doubling time is about 60 years. So clearly something's up here. What's going on? Why does it take so long? And well, the answer is that the chemistries haven't changed much, but the way we understand these systems and the way we apply these systems to other types of devices start becoming very important. Now, in particular, in my group, we focus on three main areas in energy storage: batteries, supercapacitors, as well as some recent work looking at how we can integrate systems and build up larger things. And some of the particular topics are listed here, but the key thing that I want you to take home from these different areas in our group is that with respect to batteries, we care about making batteries small. We care about making them long-lasting so that you can have many, many cycles that go into them. And we care about advanced applications. Again, thinking about things like flexible platforms or very small micro batteries, things like that. And in just very briefly in the next couple slides, I'll talk about two of these things. I'll talk about the relationship between mechanical and electrochemical properties, as well as some advanced laser processing and embedding of micro batteries. In the case of supercapacitors, what you can think about is the way we try to control the nanoscale structures. We try to optimize the size scale of these materials. We try to reach very high powers, make these systems faster. And again, we look to novel applications. How can we implement small-scale ultracapacitors, maybe flexible ultracapacitors, things like that. And finally, on integration systems, we look at questions like how do we integrate storage with alternative energy? How would you put a battery with a windmill or a wind turbine? What type of battery do you need? And also hybrid types of systems for small-scale applications. And in the case of supercapacitors, I'll just very briefly talk about these two topics on optimizing the architecture, as well as, again, some advanced laser processing. So let's start off on batteries in this lightning-quick tour of electrochemical energy storage in 2 minutes here, right? There's a real common misunderstanding about batteries. People think that they fail because the chemistry dies or the battery gets used up or things like that. But when you're talking about rechargeable batteries, the typical mode of failure is actually mechanical in nature. You can think of the laptop batteries that were blowing up, a little while back. That's clearly a mechanical failure. But you might think of a flexible battery where you bend it, maybe some kind of fiber. But this is also true in fixed batteries. And the way to understand that is that lithium batteries, the ions have to intercalate into the host lattice. What that means is that large ions have to squeeze themselves in between the planes of atoms that are already there. And so, for instance, you might have ions coming in. Once they combine with their electron, this whole thing grows just a little bit. Now, this could be a tremendous amount of strain on the systems, on the order of 7 to 10%. It doesn't sound like a lot, but that's enough to destroy most materials. And so it's actually critical to understand the relationship between the mechanics in these systems and how that affects the electrochemistry. And this ultimately can lead to improved lifetime. So if we can stop the system from failing mechanically, we could get this system to last longer. And so the type of experiment you might think about, you might think of a flexible battery, but as I said, traditional batteries as well. And the kind of thing we do is we might squeeze these things. We might, press on them a little bit, and we might see how they respond. Understand some of the electrochemical and mechanical interactions. So for instance, you might think of, mechanical terms like fatigue or stress or strain. But if we put that into the battery terminology, we're really looking at the cycle life. We're looking at the energy density or the power density in these types of systems. So that's sort of topic one, main area. In the case of laser processing on these systems, when you start throwing lasers into the mix, you can start doing all sorts of novel types of changes to the materials in the system. And one particular thing that I want to talk about is a laser direct write embedding approach. And again, there's a lot of details here, but really all you need to keep in mind is that what we can do is we can use a laser to modify a surface where we want to put a battery. We can drill a hole or something. We can then print a battery directly in that hole and cover it up so you couldn't even see the battery after the fact. And so here's a picture of it over here. This is the subject of a recent patent of ours. And you can see here's a dime, here's a picture of the battery. If you look at it on the side, you might have an anode, a cathode, all embedded within a substrate. So you wouldn't even see the thing, very small. Here's some other general pictures. But in general, when you start throwing laser printing methods into the electrochemistry, you can start actually making real systems, real devices that have significant amount of energy density as well as power density per unit area. So small scale applications, once again, novel types of implementations of energy storage. Okay, so that's the quick bit on batteries, the quick thing on supercapacitors. Many of you might not know what a supercapacitor is. Basically, you could think of a supercapacitor as kind of like a battery and kind of like a capacitor. Okay? It's very fast like a capacitor. It can give up its energy very rapidly, but it can store a lot of energy just like a battery. And basically, the way it works is you have a really high surface area. If you put a lot of surface area, you have a lot of place for these chemical reactions to occur. And there's various different types of flavors, details. But in general, one of the things that you're really striving for in these systems is how can I engineer a material that has a very high active surface area that I can somehow process into an appropriate device that I'm interested in. And so, supercapacitors have a number of advantages over batteries. This was a slide I put together for an animal tracking symposium. But basically, they have a greater cycle life. They can cycle many, many times. They have very high power. They're very good at charging and discharging. But they have a relatively low energy density compared to batteries. They have a shorter shelf life. So in general, the way to think of these systems is to think of a Ragone chart like this. And so you might think of fuel cells as being very high in energy but low in power. Capacitors are somewhere in the middle. And so we play all sorts of games with these systems trying to make them better, trying to make them more useful in various types of applications. So for instance, one of the things we do is we look at optimizing the nanostructure. How can you make more surface area for a given material? So for instance, we might use carbon nanotubes or other types of nanostructured materials. And I'm just about out of time, right? I'm long past out of time. Oh, okay. I could speak even faster.
I would be closer to you.
He's standing. He's getting when he starts pulling me off of here, right? So we could again deal with these nanostructures. We can deal with various types of situations related to these things. The last thing I want to leave you with, and it really is the last thing I promise, is again how you can further increase your ability to process these materials when you start using lasers. You can start playing some real neat tricks. For instance, I can actually create a capacitor using two lasers to basically modify the material in such a way that the end result is I have a capacitor left behind. And so all of that aside, let me just conclude with leaving this slide up here to tell you a little bit about the kinds of things we do. And thank you for listening to my rambling here. And I'll be around and we can chat later if anyone has interest.